Alright, so this lesson is on frictional forces. It's Unit 1 Dynamics and Lesson 12, this handout here. So we've gone over frictional forces in grade 11, but let's do a little review. So we have two types of friction. We have static friction and we have kinetic friction. Okay, do you remember what each one means? Now, static friction is, well, let's just go over friction in general first. Friction is when you have two objects, right? And for example, if their surfaces are moving across one another, there's going to be frictional forces. Frictional forces always oppose the direction of motion. Or I should say kinetic friction always opposes the direction of motion. So if you have two objects in motion, like this, and their surfaces are moving across each other, this is kinetic friction. And you can see that if you sort of throw it or sort of slide a textbook on a table, friction will bring it to a stop, and that's kinetic friction. Static friction is a little bit more tricky to understand. So I have it written here that static friction is required to start a stationary object moving. So for example, let's say you have a box here, and there's a fridge, and you're trying to push the fridge across the table. I don't know, maybe to clean the floor underneath. Right? That fridge is very heavy. And so as you're trying to push it, it's not moving, but you're applying a force. If you're applying a force and it's not moving, there must be some opposing force, equal and opposite. In this case, it's static friction. And I have over here that static friction is greater than kinetic friction, but I also wrote static friction max is greater than kinetic friction. Why did I write max? Well, look at this diagram. Let's go back and pretend we're pushing the fridge. Okay, so on the bottom we have our applied force, and on our y-axis we have our frictional force. Now as our applied force gets greater and greater, so we're pushing the fridge, right, and then we're pushing it harder, and then maybe a friend comes in to help push it, the applied force gets greater and greater and greater and greater, and so the static friction force matches it. Okay, and it's going to match it until a point. Once it reaches that point, the maximum value of static friction is going to start moving, and now we're going to have kinetic friction. Now kinetic friction is mostly constant. Right? It doesn't matter what speed you're moving it at, that kinetic friction is very constant. This is different from air resistance. Air resistance does matter how fast you're moving through a fluid, but for kinetic friction, it doesn't. But this is also why I said the maximum value of static friction is greater than kinetic friction. Because if we look down here, at these points on the graph, those are all still static friction, and they're not greater than what kinetic friction would be. And it's only that value just before the object starts to move. So let's go over another example. And this is where things get a little bit tricky, is a ball. Let's say you have a ball rolling, like let's say it's rolling across the surface. It's hard to show you a table. Well, let's say it's just rolling. That's a terrible demo, but it's rolling. Let's just use our imaginations. It's rolling across the surface. Okay, so you roll a ball across a table. What force is actually, or what force of friction is actually present? Static friction or kinetic friction? Think about it. You have to pause the video. Go ahead and pause the video, but I'm going to give you a hint. I'm going to take this marker, and I'm just going to make the screen bigger so you can see what I'm doing. Okay, and I'm just going to put a little black dot there. Hopefully a lot of it so the ink is still wet. Okay, and then I'm going to roll this over the whiteboard. And again, okay, it might be hard to see on the video, but there's a little dot there. Okay. I can color it in for you. There's a little dot there, and there's also a little dot there. But that's it. It's a dot, not a streak. So think about it again. Now let's say these are like wheels in your car, and they're rolling just like this, and then you hit the brakes. When you hit the brakes, it stops the the wheel from rolling. And of course, it's going to skid on the ground. So let me draw this little dot on here again. Let's say it's rolling, and right once we get to the dot, we hit the brake and we skid. And it's kind of hard to see in the video, but there's a line that goes all the way across like that. All right, now let me ask you again, which force of friction is actually present here? Let's do the first one, where the ball or the tires are rolling. Okay? In this case, it's static friction, okay? Because the two surfaces are not moving across each other. Right? The ball is rolling, but they're not sliding across each other. Okay? In this case, the ball stops rolling and it's sliding. Now there is a lot of other things that occur here, because there's a lot of other types of friction other than static or kinetic. There's also something called rolling friction, and also due to gravity, right? Any ball, no matter how hard it is, even a pool ball, is going to deform a little bit. Right? You're going to get sort of a little indentation on the part that's actually touching the surface, and that indentation will actually cause your system to lose energy and cause the ball to slow down. So that's kind of a question I get a lot. If static friction is present, well, static friction, think about when you're walking. Now when you're walking, you push back on the ground, so the ground pushes forward on you. That's actually static friction. Static friction is pushing you forward. What about when I take this ball and just move my hand? My applied force is up. So what force caused the ball's motion to change to move horizontally? In this case, again, static friction. Right? When I move it this way, right, my hand wants to move along the surface, right, and push the ball. Well, not push the ball, but if there were no friction present, then my hand would just slide under the ball and the ball would fall. But because there is friction present, friction is holding it in place, and friction is actually directed forward. That's why when I said friction always opposes the motion, I corrected myself and said, no, kinetic friction always opposes the motion. Static friction doesn't. Okay, when you're walking, it's static friction that's pointing forward, and that's causing your, I've sort of gotten all fuzzy on the camera here. There we go. It's static friction that's actually pointing forward, and that's causing that forward change in motion. Same with this. As I move it this way, static friction is causing it to move in this direction because static friction is in that direction. Okay, similarly, when the ball is rolling, static friction is actually in that direction. Right? And so I get a lot of students asking, well, if the only force is in that direction, there's nothing to slow it down, and so a ball should continue to roll forever. Yes, if we only considered static friction, yes, but again, there are things like rolling friction, right, and the loss of energy due to the fact that the ball gets slightly deformed as it's rolling across the surface. Okay, so there are other things there that cause it to eventually slow down, but I think you can tell that if you were to take a ball and a textbook, and let's say you took a bowling ball, something that would weigh the same mass as the textbook, and you gave them an initial force identical, I think it's clearly that the ball is going to go a lot farther than the textbook would, right? Because those losses of energy are so much smaller than what kinetic friction would provide, and so the ball travels a lot further. But yes, it does eventually come to a stop. Okay, now this one, when we hit the brakes and our wheels were skidding, right, notice that the two surfaces that are in contact were now moving across each other. Now this is kinetic friction. If the two surfaces in contact are not moving across each other like a rolling ball, that's static friction. It's a little bit more tricky to understand. Let me go back to the PowerPoint. All right, so you might remember these equations from grade 11. Right? Force of friction is equal to a coefficient of friction times the normal force. Now we could be talking about kinetic friction, in which case that equals a coefficient of kinetic friction times the normal force, or we might be solving for a static friction. We have two different coefficients, one for static and one for kinetic. Let me make the screen big again. Okay, now static friction, the coefficient for static friction, just like you saw in the PowerPoint, is greater than the coefficient for kinetic friction. There's something else I want to mention about this equation. This is a magnitude equation. Okay, there are no vector signs. Usually there's no vector signs because I'm lazy to write vector signs, but in this case there's no vector signs because this is the magnitude of those vectors. I mean, think of it in the case of if they were vectors, would this equation make sense? This is just a coefficient, just a number, right? A number multiplied by the vector is simply going to change its length. That's all. Right? If it's a negative number, it will change its direction in the opposite direction, but the coefficient of kinetic or static friction is never a negative number. It's always greater than 0. So that means it's just going to change the length. But kinetic friction is always along the surface in contact, and normal force is always perpendicular to the surface in contact. Would that make sense? That just multiplying by a number would cause the vector to change perpendicular? Just no. Okay, it does not make sense at all. And that's because this is not a vector equation. It's a magnitude equation. It'll help you find the magnitude of kinetic friction or the magnitude of static friction, but the direction you're going to need to figure out yourself. Okay, so don't start throwing in negatives for normal force or negative for friction just because that's what your coordinate system is. Okay, don't sub in any negatives. I think if there's anything else I want to mention. I don't think so. Let's go back to the PowerPoint. Okay, so this leads us to our example. Now I hope everybody tried the homework from yesterday's lesson. I made a video for today's challenge question. The challenge question is similar to question 10 from yesterday in your textbook, except 2 of the inclines are angled and there's friction. So I made a separate video, which is more of a whiteboard animation video that goes over this challenge problem. So if you're having problems with question 10, going over this challenge problem will certainly give you ideas for how to proceed with question 10, but make sure you can do it. And if you want to challenge yourself, go back to question 10 and add a frictional force. If you want, say, the coefficient of kinetic friction on the surface is 0.3, right? And then try solve for acceleration again. But for this lesson, we're going to go over just one question with 4 parts. Here we have a 3 kilogram block. It starts from rest at the top of a 30-degree rough incline and slides a distance of 2 meters down the incline at 1.5 seconds. Find the acceleration of the block. So again, we're still going to use that algorithm of how to solve these forces problems. And it also helps to solve any problems, right? First, read the question. That makes sense. Next, we're going to draw a picture. Okay, so we have a 3 kilogram blocks, and we have an incline. Let's make an incline, which is at 30 degrees. I'm just going to write theta equals 30 degrees. We have a block. Starts up here, slides down the incline, starts from rest. So let's write that information down. Initial velocity is 0. We know the mass is 3 kilograms. Anything that you can pick out from the question, write down here. Slides a distance of 2 meters. So that's a displacement of 2 meters. In 1.5 seconds, so in a time of 1.5 seconds. Find the acceleration of the block. So the next step would be to draw a free body diagram. Well, we only have one object, that block, so let me just draw the free body diagram right there. And let's make this bigger again. Keep forgetting. So what forces do we have here? Well, we have gravity down, mg. We have the normal force this way, Fn. And now we have friction. Right? It doesn't tell us what the coefficient of friction is, but if it's sliding down this way, if it's sliding on the surface, do we have kinetic or static friction? We have kinetic friction, and it's going to be opposing the motion, so this way. All right, so there's our diagram. Now we need a coordinate system, and again, I say choose a coordinate system where one of your axes is parallel to the direction of acceleration. So in this case, our coordinate system, since acceleration is down the ramp, let's choose an x-axis where the positive direction is down the ramp. And we'll choose a y-axis perpendicular to that. So there's our coordinate system. Now the next step says to use Newton's second law. Now this says find the acceleration of the block. Now we can try that. Let's try Newton's second law. We go the sum of all forces in x, since acceleration is in x, equals mass times acceleration. And what forces do you have in x? Well, we actually forgot to put gravity into components, so let's do that because it's not aligned with our coordinate system. So this is theta, so this is mg cos theta. This is mg sine theta. And we actually have two in x. We have this component of gravity and friction. So we can split up our forces in x to be mg sine theta. Friction is in the opposite direction, so minus fk equals ma. This leaves us with a problem. Now, m we know, g we know, theta we know, m we know. But we don't know what the force of kinetic friction is. Now, I could write the equation for kinetic friction. So here we have mg sine theta. And instead of writing minus fk, I can write the coefficient times the normal force, which equals ma. But I don't know the coefficient or the normal force. Now there is a method to solve for the normal force, but let's just take a pause there, because even if I solve for the normal force, I'm not going to know the coefficient. Right? So how am I going to figure out acceleration? Well, let's go back and think about this. It's actually giving us displacement, time, and initial velocity. Sounds like a question from the first chapter, like a kinematics question with our 5 equations of motion. Can we use those? Of course we can. Why not? Physics equations work in all situations, right? They try to describe nature. If they don't work, then they're not describing nature, so you can't use them. Okay, so we have 3 variables that we know, and we're looking for a fourth, acceleration. The one we don't know is final velocity, so let's use the equation that doesn't have final velocity. Delta d equals initial times time plus 1/2 a delta t squared. Okay, initial is 0, so that whole term is gone. So we're left with delta d equals 1/2 a delta t squared. And all of these values are positive. Well, times a scalar is positive. Right? Displacement and acceleration are both positive because they're both in our positive x direction from what we chose. We just need to rearrange to find acceleration. So acceleration is 2 delta d over delta t squared. Now we can plug in our numbers. 2 times 2 meters, that's 4 over 1.5 squared. Calculator. Whoops. 4 divided by 1.5 squared. 1.78 meters per second squared. Okay. Now, I should round that off to 1.8 to use proper significant digits, but this is only part A, and I'm probably going to need that acceleration, so I'm just going to keep an extra significant digit. Now, part B says find the coefficient. Oh. Well, it looks like what we did before isn't a waste, is it? Because now that we know acceleration, if we can just find normal force, we can solve for the coefficient. Okay, great. So I just need to find the normal force. let me just erase what we did for part A, and we're going to try and find the normal force. How are we going to find the normal force, though? Well, it's a y component, so let's write Newton's second law in y. Sum of all forces in y equals mass times the acceleration in y. What's the acceleration in y? There is none. It's not flying off the ramp, right? It's sliding down the ramp, and that's our x direction. There's nothing moving in y, so 0. Well, what forces do we have in y? Well, looks like we have the normal force and a component of gravity, and that's it. Okay, so we have Fn minus mg cos theta equals 0. So rearranging, Fn equals mg cos theta. So what I'm going to do is I'm going to sub this value into Fn. When we do that, we get something really cool. I'm just going to erase this diagram so I have some more room here. So you have mg sine theta minus mu k, and instead of Fn, I'm going to write mg cos theta, which equals ma. Now here's the cool thing. Yesterday we kind of did an example where if a block is sliding down a ramp with no friction, we said it doesn't matter what the mass is, it'll always accelerate with the same rate. Well, look at this. Now that we've added friction to that problem, there's still a mass in every single term in our equation. And so it's going to cancel. So even if there is friction, right, the object will accelerate at the same rate as any other object, as long as mu k is the same. Right? Obviously, if you have two objects that are different materials, they will have a different value for that coefficient of friction, and therefore the acceleration will be different. But if they're the exact same object with simply different masses, they'll accelerate down the ramp at the same rate. Okay. Actually, I'm going to take a sidestep here because I once had a student ask me an interesting question. If you are on a water slide, certain water slides require you to be of a certain mass to go down. So if mass doesn't matter, why is that there? That's a really good question, and the answer is terminal velocity. Okay, now we kind of talked about terminal velocity when we talked about acceleration due to gravity, right? Every object will accelerate and increase their speed faster and faster until the air resistance acting on them is equal to the force of gravity down, and therefore the system reaches equilibrium and the object no longer accelerates. This is true when you're going through any fluid, air or water, right? And someone who is more massive will reach a higher terminal velocity. Right? So in that case, when you go down a water slide, you obviously don't accelerate. If it's like a very long water slide, you don't accelerate throughout the whole water slide. You eventually reach a terminal velocity. Right? And if the water slide has a loop, you need to be going fast enough to make it over the loop. And if you're not massive enough, you won't have a very large terminal velocity and won't go fast enough to make it over the loop. So it's an interesting problem because in the real world there's lots of variables, but of course in high school we say let's ignore this, let's ignore that, let's ignore this. But if you continue on to physics, you get to start taking all of those extra things into account. Of course it gets more difficult, but also gets more interesting. So let's continue with this problem. We are solving for mu k. Right now we know everything else in the problem, so we just need to solve for mu k. So rearranging the equation, can have mu k g cos theta equals g sine theta minus a. Okay, and then mu k equals g sine theta minus a all over g cos theta. There you go. Now we just need to plug in our values. and I think I already have it listed on the PowerPoint. Yeah, 0.37. What's the units for mu k? Just out of curiosity. Okay, think about it. What are the units for that? Meters, newtons, newtons per meter? No units at all. Okay, it's dimensionless, right? It's a ratio. If we take our equation like kinetic friction equals mu k times Fn, what mu k actually is, if we just rearrange that, we get Fk over Fn. It's simply a ratio of the value of the force of friction over the force of normal. That's all it is. Because when you think about it, normal force is simply a contact force. Remember, a lot of people think it's always opposing gravity, but no, it's not. Right now, if I'm leaning up against the wall, I have two values of the normal force. The wall pushing forward, and of course I'm sitting on the chair, so there's an upwards force from the chair as well. Right? The reason they exist is because there's a contact force. Right? If I were just in free fall, gravity is still acting on me, but there's no normal force because I'm not in contact with anything. Okay, and what's friction? Kinetic friction. That's also some kind of contact force, right? You don't have friction unless you have parts in contact with each other. Right? Obviously, if I'm going like this, there's no friction there. They have to actually be in contact for you to have friction. Right? Now, if I increase the normal force and really push inwards on them, it's a lot harder to do this up and down. Increase the normal force, increase normal force, increase kinetic friction. But if the objects remain the same, like my hands, the value of that coefficient will stay the same. Right? Now, if you want to change the coefficient, you need to change the properties of the two surfaces that are actually in contact. Right? Such as, you could have rubber on asphalt, or you can have rubber on ice. Right? That's what changes the coefficient. Okay? A lot of people also think that surface area changes the value of friction, but it doesn't. There's no surface area anywhere in this equation. Right? Now, when things get a lot more complicated, yes, surface area does play a factor, but if in an ideal situation, no. Okay, and we did a lab like this in grade 11, or possibly just a demo or a quick activity to actually assess whether or not surface area plays a difference. Let me just grab a textbook. I'll quickly explain this again. So here's a textbook. It's my astronomy textbook. If you're interested in astronomy, good textbook. But anyways, so let's take a surface. I wish I had a table here. Take a surface, right? And let's say my hand covers the whole surface area of the textbook. I don't think I have anything else now. And I'm pushing this across. Okay, now this entire surface area is in contact. Imagine with a big hand. This entire surface area is in contact. But the normal force, or the weight or force of gravity over any point is, I don't know, let's say 10. Just give it a number. Let's say 10. Okay, and let's say there are a certain number of points that we want to consider. Now, if I do this, right, over a certain point, you no longer have a small value of weight or force of friction or mass above there, right? You have a lot more. So you have less surface area in contact, but more force over that surface area. And it's a great ratio that always matches, right? Whether you do this or this. And so surface area isn't going to play a major role in calculating the force of friction. Okay, let's go back to the question. Part C, it says to find the frictional force. Oh, that's not too bad. We've done pretty much the hard work already. Here you have the normal force, and the frictional force, well, there's our equation right there, where Fk equals mu Fn. And Fn we know to be mg cos theta. Okay, and we know everything there. We know what mu k is now, we know mg, and we know theta. So we can calculate what Fn is. And I have that in the PowerPoint, 9.3 newtons. Now the last part says the speed of the block after it has slid 2 meters. So this sounds like a forces problem or a motion problem. It's asking for final velocity. Sounds like a motion problem. And since we know all other 4 variables, initial velocity, acceleration, time, and displacement, you can pretty much choose your favorite equation. Of course, except for the one that doesn't have final velocity. Then what would you solve for? So let me just write final velocity equals initial velocity plus a delta t. Initial velocity is 0, and so final velocity is just acceleration times time. That's it. And in the PowerPoint, I have the answer for you. It's 2.7 meters per second. Okay, so that's it for that lesson. Make sure you look at the challenge problem and make sure you're okay with question 10 from yesterday's homework. And if you need to, remember I have that other video that goes over this challenge problem.